So
Yeah.
in the last previous session, we were talking about we covered target engineering, right? You know, how to do some transformations to the target, especially if it's supervised learning, you know, a label or a continuous feature that we're going to try to predict. Then we spent some time in dealing with missing values, which is a chapter, you know, on its own. So we just, you know, kind of, you know, touch the surface of it. Now we're going to enter into what is called feature filtering. Also, you could find it as feature selection. Okay. So let's see what that is about. Okay, so in feature filtering, what we are doing, let me go to the book. Okay. What we're doing is trying to filter, okay, or select the most informative, okay, predictors for our model. And the author, you know, makes the case, illustrating with these charts, what is the effect of, for example, adding a non-informative predictors to the model, the effect on the metrics, for example, the RMSE, within different models. He, you know, divides in linear model, right? Right here, linear model, nonlinear models, and tree-based models. As we can see, at least in this chart, the tree-based models and some of the regularization regression models like Lasso or Ridge, they do well trying to, you know, wean out that non-informative predictors within the internal mechanisms of the algorithm. But even though maybe in the metric there won't be, you know, a detriment effect on those, you know, algorithms, still, when you go to the performance, right, in terms of the time that takes the training, he performs here at tenfold cross-validation. So when you do that, then basically all the models, you know, start suffering when you add those non-informative predictors, okay? So it's good, at least, you know, to get rid of some of the predictors that have zero variance, right? Or near zero variance. And where we call zero variance is when there's a feature or a variable that has a constant, you know, number or label, okay? For example, if you are dealing with a category called with a variable called year, and the year is all in one specific year, then that will be a constant. So you could eliminate that because there is really no variance, and the variance is the one that you know, associates the variable with the predictive power. Okay, if there's no variance, then there is really no predictive power. All right. So going back to the notes, okay, we have in Caret and also in tidy models, we have a function called near zero variance. And I, you know, check what is the, you know, what is the you know, the characteristics of this, you know, function near zero variance. And what it does is that it checks for features, especially categorical features, with this cutoff ratio, 95:5. And what it says here in the frequent cut is that the cutoff for the ratio of the most common value to the second most common value. In other words, if all the labels are concentrated 95% or more in one of the labels in the category of variable, that variable is basically near zero variance. In other words, you know, it has a little variance in terms of the composition of those labels in the categorical. In terms of numeric, what it does here is that it has a unique cut argument, okay? And its default is 10. And what it says here, that is the cutoff of the percentage of distinct values out of the number of total samples. So it's going to do like a count, okay, of the distinct, values or numbers that it has that continuous feature. And then it's going to say, okay, if everything is grouped in one value in terms of 90% or more, that's going to become also a near zero variance, okay? And it's a candidate for, deselection or dropping or removing, okay? So if we apply this to our AIMS train data set, and then we convert it to a table, and then we filter by the NZV, okay, which is the non-zero variance indicator. What we'll see is that some of them, even though they are not zero variance variable, in other words, it has some, distinct labels or values, the non-zero indicates that those could be more than 95% grouped in one label or more than 90% in one specific value, okay? A word of caution, okay, here. These are candidates, for removal. But as we will see, you could extract some information from these, features in terms of, converting them to flags, for example, so that you can extract some information and then drop the original feature. And we'll see an example with the street porch, okay? One of the variables that are non-zero variance, but you can extract some information out of it. The section is very short. It's just an introduction to tell you, be aware of non-informative predictors, okay? But as again, this could be a chapter, in fact, many chapters, on its own. And the feature filtering methods that exist around, the data science, machine learning field, they are grouped in 3 categories. For example, they are grouped in filter methods, okay? Zero variance, non-zero variance analysis, and correlation are in this group. The correlation is when you have features that are very highly correlated, and maybe you want to discard one of them, okay? To avoid, in regression, to avoid the multicollinearity, effect. Then you have wrapper methods, okay? When you do a forward selection, backward selection, in other words, you start with all the predictors, and then you take one and see, what is the effect on the metric. That's basically backward. Or you can start with one predictor, the most informative, and then, keep building until you see which are the optimal number of predictors for a specific metric. Also, you have recursive feature elimination, which also works with tree-based methods to do, forward and backward elimination, both of them. Then you have embedded methods, okay, which what they do is that in regression, you have what is called a lasso L1 or ridge L2, and what they do is penalize those predictors that maybe they have a high correlation with other predictors, or they're not informative, and they get penalized and they get basically discarded within that regularization, okay? And you can learn a little bit more about this. I included an article, okay, when you can, check a little bit more about this, okay, which is Introduction to Feature Selection Methods. And, it gives you an example of each of the ones that we have been discussing here. Okay. Any questions so far? Good.
Yeah, good. It's good. Actually.
Hello, I have a question.
Oh, okay.
Oh,
who's there?
Hello, Angel. Nice to meet you.
Oh.
Okay, excellent.
Okay, we have a new
new
guest
participant
here.
Okay, great.
Welcome.
Welcome.
Yeah. Thanks. Yeah, I have seen wrapper methods for linear regression. Have you applied or know if study model have options to apply to another machine learning methods?
Okay, you were talking about linear regression there?
No, I'm talking that I just have seen the wrapper methods just for linear regression. And I would like to use that method for another machine learning tools. And I don't know if there are options for other machine learning methods.
Yes. For example, in linear regression, these embedded methods, for example, okay, usually are applied, and they are really called regularized methods, regularized regression. But yeah, you can use, for example, zero variance, non-variance. They are, algorithm agnostic, okay, because they depend on the structure of that particular, feature or variable. And you can use in this one recursive feature elimination. You can use it with a tree-based method as the engine that is going to do the backward-forward selection and then give you an optimum set for your model, be a linear regression if it's a continuous variable or a classification, problem.
Do you know the function that performs that action?
What was that?
Do you know which function performs that action?
The RFE?
Yeah.
The RFE, yeah. The RFE, recursive feature elimination, it can use random forest, for example, and it can use gradient boosting.
Okay.
Those are the two, methods that I'm seeing most common. The problem with recursive feature elimination is that if you have a big set of features, let's say 1,000, for example, it's going to take a while. Okay, it's very computing intensive. So yeah, you have to be careful. I ran it, one example with an old laptop, and it took about 8 hours.
Wow.
To give the results, and the results were not that, were not that great. So be careful with that one.
Okay, thanks.
Okay, but yeah, you can use also Lasso and Ridge. I believe in XGBoost, they use for the features, filtering. Internally, they use these methods too. Okay.
Yeah.
And what
Actually,
they do is that they penalize instead of selecting, trying to, for example, in forward selection, what you do is you start with the most informative, let's say the most correlated feature, and then you start adding. And then you check a metric, for example, RMSE if it's a continuous variable, or accuracy if it's a classification problem. You start checking what is the output of that metric. And if the metric goes down, that means that what you're adding is is an informative predictor for that model. In Lasso and Ridge, the embedded methods, what they do is they penalize. Okay, they have a formula that they penalize some predictors that are not informative or they are highly correlated. Okay, and that one, works with a regression, a classification, and also with I know that XGBoost uses it internally, for that purpose too.
Yeah, great. That's great to know. Thanks.
All right.
Yeah, actually, for reference, like in case of the repo method, like forward selection and backward eliminations, we actually in R, there is actually a function for step.
Right.
So yeah, we can use that one to optimize, to select the variable or maybe features that optimize the model. But the thing is, one of the problem of the forward selection and backward elimination is just kind of these actually function actually focusing on the optimizing the model based on the some maybe AIC or some specific kind of a criteria.
Correct.
But sometimes depending on your research question, and then there is a very important or critical variable you have to include in your model, but maybe forward selection or backward elimination deletes that variable. Yes. Sometimes these kind of a selection or elimination method give you the too simplified modeling suggestions. So in that case, you should be very careful about depending on your research context or depending about your objective of the research, you have to be very careful about this. Which one you should be delete, because this might be one of the criteria you can use or consider when you're developing these kind of predictive model or machine learning process. But the thing is, if there is some critical variable that you really need to include in your model, but this kind of a method actually suggesting the deleting it. But the thing is, in that case, maybe you have to think about you have to follow your instincts based on your research context, or just deleting that critical variable, even if that is important. So what I'm going to say is it is very helpful, but use this one as a kind of a reference, okay, depending on your research context.
Yeah, that's very true, especially when you are explaining this to to the client or the stakeholder about the results, and sometimes they say, hey, but I really want you to consider including this. That even though the model says it's not informative or it's not helping the model, I want you to include it because I know by experience, I know that feature could be informative. Okay.
Yeah, right. Because for example, like when you're looking at the table at the top, like a data set is maybe, for example, in case of the utility kind of thing is might be the very we might think that very critical factor that affects to the housing, predicting the housing prices, maybe depending on the our research purposes. So in that case, even if it is a near zero value, we have to include this one, or maybe we have to thinking about if we really need to include these kind of things, we have to thinking about the collecting or recording this variable in a different way. That's the thing we have to be in mind. So
yeah, we're going to see an example. The numerical feature. We're going to see an example of one of them that is I think it's this one. Let me see if I can find it. Yeah, screen porch. Okay. A screen porch, it says that is, non-zero variance. In other words, they are grouped, more than 90% of the values are grouped in one value in particular. Okay. But there's an example of how to transform, how to get some information on this variable that then could be useful, to the model.
Okay. Right. That's what I wanted to talk about. Yeah.
Okay. Excellent. Okay, so let's continue with numeric feature engineering. This one, we already, because we're working with the aims, and the aims is a regression problem. Okay, the feature is continuous, the sales price. We already did some transformations, right? Using the log function, logarithm, and also Box-Cox transformation. So that could be used also for the predictors if they are highly skewed and your algorithm needs that distribution of the predictors to be more of a Gaussian or normal distribution, then we can use the same methods. It's very, the author tell us that tree-based models, okay, usually are quite immune to this type of problems, okay? Especially, for example, numeric features. But there are some models, what they call, they use a distance from a parameter, for example, for the mean. So for example, generalized linear models, regularized regression, KNN, K nearest neighbors, support vector machines, and neural networks, they're very sensitive to the composition, okay, of that numeric value. And apart from trying to get more Gaussian, also you need to do a standardization, normalization on the scaling of that feature. And there's an example that the author gave us, okay, here, where he generates using different distributions. He used a uniform distribution here. He used a log normal and then a normal, right? A distribution. And then what he does is that he generates random numbers, okay, for those three distributions within some parameters. And then he also uses the scale, base R, scale function, to scale that numeric feature to a standard scale, okay? A standardization scale. So the result is this one, okay? These are the original values, okay? These are the original values. As you can see, the scales are totally different from each of these features. And that's going to create a problem for what we call the distance measure algorithms, because depending on the scale of the numeric feature, the algorithm is going to give more weight to big numbers than small numbers, okay? So if you have a scale, for example, salary usually, could range from, let's say, 20,000 to 150,000, right, per year, annual salary. So if you compare that to then, let's say, years of employment, okay, with years of employment could be from 1 year to 20 or 30 years. The scales are very different. So in order for the algorithm to give them the same, the same weight, you have to scale them, okay? And one of the, functions that you can use for scaling, base R scaling, it gives you then the chart in the right that is going to be scaling those numbers, but in the same, in the same range. In this case, from -3 to 3, which is kind of a normalization that we're using, okay? And this is, a very common step if you work with tidy models, okay? When you do a recipe, you use a function called step normalize, which combines the scaling of centering that feature, okay, centering to 0, and then scaling the variance to 1 standard deviation, okay? So it does, both of the steps that you have to do, it does it in one. And even for tree-based models, is something that it helps. It doesn't hinder the model. It helps it. Or also, although they are not required, the tree-based models don't require you to normalize or standardize those numeric features. Okay. Any comments, questions?
Yeah, that's right. I know that is another step function, that is a step range, and
yeah,
that is another normalized function. But in this case, rather than just saying the distribution, it just like restrict the range of the value. So if you are running a k-enables model, and you have, for example, some feature encoded with 0 and 1, and you have also numeric features, that step, I think, is the best in order to range numeric values between that range of 0 and 1, so the cadence neighbors doesn't take the other one, because in this case, even though you normalize the numbers, the range is between -2 and 3. So yeah, those features will have a high importance if you compare with the dummy variables that you create for categorical variables.
Exactly, but remember, this is only for numeric, okay?
Yeah.
Categorical, you know, we can deal with that later. But this one is only for numeric. And usually this is the, you know, the recommended, at least in the data models framework, this is the recommended way, you know, to do it. But yeah, you can do it 0 to 1, min, max, you know, there are different methods. You're right. Okay.
Great, thanks.
Okay, so let's go to the categorical, okay, which is the other type of, you know, general data type that we have. So the thing is here that most of the, you know, algorithms that we're going to be seeing in the chapter, they require the predictors to take a numeric form. In other words, you have to transform these categorical features into numbers, okay? There are some exceptions. For example, there are some tree-based models that can handle numeric or categorical features as they come, okay? They don't need transformation. For example, there is an algorithm called CatBoost, okay? Which is very popular in cat competitions. They can handle categorical, you know, they have an internal mechanism, you know, to convert those categorical features to numeric features. You don't have to do it in the pre-processing phase. But usually, tree-based models can benefit, you know, from these pre-processing categorical features. So one of the examples that the author gives us is that we can lump the levels of the observations within categorical features, so we can then get a reduced number of labels that eventually will become features with one-hot encoding, dummy encoding, etc. So in this example, using the aim strain, right? When we do a count, right, of the neighborhood feature, and we arrange it by ascending order, you know, the counts, you will see that some of them have, you know, a very small count, okay? 1, 2, 3, etc. So one of the things that we can do, and we're going to use the recipe function, okay, from the tidy models framework, and we're going to use this function, this helper function, step other, which what it does is that it lumps the categorical labels, the levels, where the threshold, okay, and you can assign the threshold, is going to be less than 1%. So for example, if landmark is less than 1% of the total count of, you know, of levels, you know, that category has, then it's going to be lumped into the other category. And you can specify which category you want, you know, the name of the category that you want to assign. So what it's going to do is that in this case, when we do a prep, we have, you know, because we're creating here a recipe, so we have to do some manipulation here with some functions to get the information from the recipe. So if you do a prep, you do a bake, right? And you assign the new data as the aim strain, which is the data set that we're working on. You do the count and you do the ascending order. You see that it starts with this one, okay? Meadow Village. In other words, the ones that were less count than Meadow Village, they got lumped, okay? And they got lumped here in other, okay? So you can reduce the number of levels of your categorical variable to a certain amount, then when you do the one-hot encoding or domain encoding, you will have less, less features. Because remember, these are going to be converted especially to numeric, and the one-hot encoding is going to convert each of the levels to a feature, okay? So let's say that we have 100. If you leave it like that, you are going to have 100 features, okay? Or 99, depending on how you do the domain encoding. But if you can reduce those 100, okay, to let's say 80 or 70, then you'll have 30 less, to worry about, okay? And for the numerical features, the author gives an example, okay, of the screen porch. We have seen this feature already in the non-zero variance, okay, that it qualified as a non-zero variance. And the reason is that most of the values of screen porch are zero, okay? We have 1,869 out of, 2,000 observations, more or less. And, they're lumped, right, in this value. The other values were out, all over the place. So one example that the author gives us is that using, again, the recipe, we can create what is called, a bin, right? In other words, we can group all the zeros in one label, and then anything more greater than that zero, we can group in another label. In other words, we're converting this numeric feature into a categorical feature, using a bin technique. And this is the step that is converting that screen porch into the category. So if the screen porch is equal to 0, then we're going to assign with the new feature, we're going to assign 0, but this 0 is a label, okay? It's not numeric, okay? That's what it's between quotes, right? It's a label. Then if it's not 0, we're going to assign it to this other label, which is greater than 0. And then we're going to convert that string, that character type, into a factor, all right? So when we apply again for the recipe, we apply the prep, the bake, do the counting, and do the arrangement, we'll see that now we have grouped all those values, we have grouped it into levels in a category, which is 0 and more than 0. And it could be more informative than what we had originally in this, way as a numeric variable. Okay. I'll give you a warning, is that the author doesn't use tidy models, and the way that he tried to do this, for some reason, it didn't work. Okay, apparently there was a change in this function. Okay, step other, that it doesn't it doesn't accept, okay, numeric features. They have to be categoric. Okay, I'll show you here. If you do step other, okay, let me see if I said it right. Step other. Okay, here we go. Okay, recipe. One more. It says train logical. Somewhere here, let me see if I can find it. Okay, somewhere here it tells you that it needs to be, a discrete variable. It won't accept, okay, in the selections here, it won't accept right now a numeric. And in the book, the author uses that function. Okay, so be careful with that one. Okay, so that's why I had to, kind of use other functions to try to mimic what the author was trying to, accomplish here. Okay, but this is a good way to, convert those numeric features that maybe have been categorized as non-zero variants, converted to this, the categorical features using this bin technique, and then try to use that information into our model instead of the original feature. Okay. Question, comments?
Okay.
Yes. In here, maybe let me type on, because in this case, actually, I prefer to use, there is a R function called within. Have you heard of the within functions? Yeah. Like this, like MS train, and then we can say about the, like, okay, porch, screen porch, flag, none, and then when we like this, like and then what's the screen?
Are you typing something in the screen?
Yeah.
Okay,
you cannot see that?
No.
Okay, hold on. Let me maybe I think let me finish in this one. Okay, hold on. I think and then
yeah, I believe that you can do it with cut. Okay.
Yeah, cut or within function is much better. Like hold on. Porch flag. Because within function is actually kind of like a base R.
Yes.
Kind of functions, but the thing is, this one might be much better, I guess. Hold on, is that? Yeah, like this.
Okay, here we go. Okay.
Yeah.
Yep.
So these are the much simpler way, because it's in here. Actually, it steps the 2 steps. Like we creating this one, decoding one, and then I try to baking it. But we just directly setting up these kind of a categorical approaches right here, like this. Or maybe if you can say about the AMOS and train, and then maybe screen, porch, flag, and then we can, it's a dummy variable. So if we can say about the if else function, like if it is true, we can say 0, and then it is not true, like this. So this might be the possible way to do that, but we don't have to keep using about the recipe or these kind of functions to do that. So, or maybe some kind of a tidy, because I know that sometimes in our community there is a lot of people who are big fan of the tidy model or tidy data, tidy burst kind of a data management or cleanup. But sometimes we have to make a balance just try to using between traditional one and tidy one, depending on the how simple it is. So yeah, so I just want to say about those things, because there is a much better, simple way we can do rather than try to using these 2 line of the code to making these things. So
the things that at least the tidy models gives you kind of an advantage in terms that it's engineered in a way that it avoids what is called data leakage. Okay. So for example, this recipe, right? You are using the train, right? The training data set. And we are baking with the same one, right? The same one, to get the result. But you can use, and internally, when you do the modeling, if you use the recipes okay, you can do the testing. Okay, you can bake the testing data set, and you will see that the parameters that are applied to the training set, they're going to be applied then to the testing set. And that avoids that problem of data leakage. In other words, you are not, you are not using any information from the training data set, okay, that is applied, inadvertently to the testing set, okay. And we're going to see like a framework of what we're talking about. But data leakage is very common, especially when you're working on the data set before splitting, that you're doing transformation on both the training and the testing data set. And that is not, the best practice, okay? What you have to do is work on your training set and then apply, okay, your recipes, your modeling to the testing set. Because that testing set, what it's telling you is that that is the unknown data. That is the new data that is coming. And sometimes the new data doesn't have the same parameters that the training set did. So when you apply it, the parameters to the testing set, then you will see if your model can generalize or not, okay? So I like, at least, in my opinion, I like this, framework, because it gives me a little peace of mind that I'm not going to be doing that, that data leakage, inadvertently, okay? But yeah, you can use, you can use any methods, and the book is based on Carrot, okay, which is the predecessor of the tidy models framework. But you will see that, it makes it a little bit easier and avoids the problem. One of the goals of the tidy models framework was to avoid that problem of the data leakage, okay, philosophically.
Mm-hmm.
Okay,
yeah.
so let's keep on. So we talk a little bit about the one-hot and dummy encoding, right? Mm-hmm. And this is the traditional method on how you convert your categorical variables, okay, into numeric. And probably you have seen this already, but there is a slight difference when we talk about dummy encoding and one-hot encoding, okay? So if we have this X, right, as the feature, the categorical feature, and let's say that we have A, B, and C as the levels or the labels. So the one-hot encoding, what it's going to do is it's going to transform each of those labels or levels into a feature, okay? And it's going to say, okay, if in the first row there was an A, okay? So in the feature called A, it's going to be 1. And if it was not present in other rows, then it's going to be 0. So it kind of, bins it again. But in the one-hot encoding, you're going to have equal number of features as different labels that you have in those category and the category variable, okay? The dummy encoding, what it does is that it skips one level. In other words, it gives you all the labels as feature except one. And the reason to do that is that some models, for example, ordinary regression, logistic regression, KNN, etc., are very sensitive to the effect of multicollinearity, okay? So if you have all the features, all the labels as features, they're going to be multicollinear between them. So if you take one out, okay, that's going to reduce that multicollinearity effect. So for some models, you're going to use dummy encoding, especially the ones that, are distance based, okay? Ordinary regression, logistic regression, KNN, etc. And then for other models, for example, tree-based models, you should use the one-hot encoding because the multicollinearity doesn't affect them, okay? So far, so good?
Yeah, actually, this kind of a coding is a kind of like for the especially very useful when we try to conduct a model called multi-class classification algorithm in the one of the machine learning approaches.
Yeah.
Because I frequently clean up the data like this because like for example, there is some variable with 120 different categories. We have to try to do, there is actually two ways to do that, like just using that one as it is, or we can try to converting one hot or dummy coding kind of a process, which produce the 120 column, separate column to do that. But by using those 120 multi-class column attribute, we can conduct what is called multi-class algorithm, like a set of the recommender system based on the other attribute conditions.
That's going to be a challenge, you know. You know, trying to predict, you know, those classes. I remember that, you know, I work in a project where it was a multi-class a problem, and there were 9 labels, and it was you know, it was a challenge. Okay.
Now, actually, in my project I'm working on, I actually have 116 items. So we converting those things into the dummy one, so that we can use the multi-class kind of things. Actually, the reason why we have to try to encoding like that is that actually kind of reducing the risk of what is called the data balancing problem. So so that's the reason why we actually try to do some kind of those kind of encoding process, and then using those 116 columns for our model kind of process. So yeah. Anyway,
I mean,
just go ahead. Yes.
It's a challenge, you know, it's a challenge.
Yeah, definitely a challenge.
Yeah. Okay. So apart from the one hot and dumb encoding, okay, and you can do this, you know, again, you know, with the tidy models framework, you can use this in one function called step dummy, and the default of step dummy will create what is called a full rank. The full rank is this one, is the dumb encoding. Okay, so it will give you n-1 features, and n is going to be the number of levels in your category variable. But there's a setting called one hot, sorry. And the one hot true, what it's going to give you is this one. Okay, it's going to give you all the features. So depending on the algorithm that you're using and, you know, the purpose of your how you're going to handle this category of features, this could be, you know, this could be valuable. Okay. And also remember, one hot encoding, the problem that it has is that it's going to, you know, increase what is called the dimensionality of your data. In other words, if you have, let's say, in this case, the aims already has 81 you know, features, okay, variables. Some of them, some of the categorical variables that we have seen have, you know, let's say 20, 30 labels. So if we convert those to one hot encoding, all of them, you're going to have a really, you know, substantial amount of features there that you have to handle. So one of the things that you can do is label encoding, okay? And what it does, label encoding, is that it converts those levels of the categorical variable into a numeric variable, okay? So for example, it says that if a categorical variable is a factor and it already has pre-specified levels, okay, then that numeric conversion will be in that order. So you know that the factors, what they do is that they have internally, they have a sequence, right? A sequence in terms of alphabetical or other type of sequence, okay? That's why we have in R really we have two functions. Okay, I don't know if you are aware of this. As factor, okay, is one of the functions. Okay, let me do base R here. Okay, as factor, let me see if I can pinpoint this. Okay, so you can convert your character variable into a factor using this, this function as factor. And what is going to do is that it's going to order it, okay? It's going to order it by alphabetical order. So anything that, the label that has, the character A is going to be the first one, then B, C, and so forth, alphabetically. But then there's another one that is with a, with a camel spacing as factor. And this comes from the tidy. Okay. And this also converts from the forecast package. Okay, tidy package. So this one, it converts, and then the ordering says here is based on the numerical value and consistent with base R. So what it does is that it orders the variable, I believe, you can check it out, I believe, by the count, okay, by the number, the frequency of that label, okay? So you have two ways to order it. If you order by the dot as factor, then probably you won't have this, okay? You won't have this label, this sequence, because the sequence is going to be alphabetical. So sometimes you have to check which is the order, the internal order of the factor, so that you can have those levels in the correct order, okay? So if we do mstrain and count what is called the MS underscore subclass, you will see that there is a factor, and also it has a specific order, right? It has one story 1946, newer styles, 145, etc. So if we encode this, okay, as it is, it's going to give us an order in terms of, numbers, okay? So if we do in the recipe, tidy models, we do step integer, and we prep and bake and do the counting, we're going to see that the same order that we have here, okay, for the factor is going to be reflected in the label encoding. So one of the drawbacks of the label encoding is that it's going to give you, automatically, it's going to give you an order, okay? So if the categorical variable is nominal, in other words, the order, is irrelevant, then you shouldn't use this encoding, okay? You should use one-hot encoding, because one-hot encoding doesn't takes in account the order of those levels. But then, if you have an order, an ordinal, kind of a categorical variable, then you make sure that you have the proper order of the labels, okay? And you apply that step integer function in the recipe, and then you get a numerical equivalency of the order of those factors, okay? The benefit of this is that you're not creating new features. You're just converting a label into a number, all right? So for ordinal categorical variables, the one that have orders, it's the way, is the way to, to encode them, okay? And there's an example of features in the Ames train dataset, that features that have quality as as part of the name qual, and those usually are ordinal. In other words, there's association with a label and the level of quality of that particular feature of the house. So you have a poor, you have average, you have a good, above average, etc. So you have an order that you can, set up a guide. So those features qualify very good for, being labeled, encoded in a label, a label encoded way. Okay, so here in the overall quality of the unit of the housing, you have already the order already in the embedded in the factor from very poor to very excellent. So when you do the recipe step integer, then you get those labels. You get them in the correct order numerically. Okay. Comments and questions.
Yeah, that's a great idea.
Mm-hmm.
To keep the order as part of the model.
Just make sure that when you're using this label encoding, methodology, that you're sure that it makes sense with the levels that you have. For example, if it's color, the color of the house, for example, white, brown, whatever, that doesn't have an order. Colors doesn't have an order, right? Or unless you can prove that they do, but usually they don't. Okay, so the colors, you shouldn't use label encoding, basically, in the traditional way. So you will be using one-hot encoding or DOM encoding or some other encoding. Okay, guys, it's 7:57. Okay, so we're approaching the 8 o'clock hour, the 1 hour span. So I don't think we have that much, okay, to cover, because some of this, let me see, yeah, some of this is just a mention. For example, dimension reduction. We're going to talk about that in chapter 17 to 19, especially principal component analysis. And there is a guide for the proper implementation. So what we can do, I suggest, is to cover this for future cohorts, is to dedicate maybe 10 minutes, okay, to the remainder of this chapter, to cover it, and then maybe start with the next chapter. What do you think?
That's right.
So you mean you're gonna do this rest of this thing maybe next week, and then we move to the next chapter?
Exactly, but I don't think we'll cover the hour, because
okay.
I think what is missing is about 10, at most 15 minutes. Okay.
Okay.
But it will be good information to include for our peace of mind, and also for future cohorts. Okay.
Maybe I think that you just cover the rest of the chapter 3 only. Maybe you can spend 10 or 15 minutes next week to explain all of these things. Because as I said, our goal is to try to understand in-depth understanding about the machine learning through this study group. So yeah, you just you feel free to spend the 10 to 15 minutes to cover this one. And then maybe next one is actually chapter 4 is a linear regression, I guess, right?
Correct.
So maybe who gonna do this? Because you already done a lot. So maybe because how to pronounce your name? Angel Felix Federas, right?
Yes, Angel.
Yeah. So you are new here first time today, so I don't want to give you the assignment to you to cover chapter 4. So I'm gonna do the chapter 4 right after Ricardo finishing the rest of the chapter 3, and then I will prepare for the presentations or explain to the chapter 4, and then let's see how much we can cover chapter 4 next week. Okay.
Yeah. Maybe I won't be able to come next week.
Okay. Yeah. So I will cover the chapter 4 then.
Yeah. Thanks.
Okay. Yeah. Excellent.
Yeah.
All right.
So already, so it's 8 a.m. right now. So we done today. So maybe Ricardo gonna be cover the rest of the chapter 3
Right.
For 10 or 15 minutes next week, and then I will cover chapter 4, the linear regression, next week. So have a nice Sunday weekend, and then I will see you all next week.
All right. Take care, guys.
Yeah, that's right.
Yeah, take care.
Thanks,
Bye-bye.
Ricardo.
Yeah,
Bye-bye.
bye-bye. Yeah.
Bye.